Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be learning a new topic for solving a system of equations. In the past, we've had both the substitution and elimination methods, but now we're going to learn about a different technique, a technique that's used quite a lot in mathematics, but rarely gets covered in high school algebra, and that's the topic of matrices. We're going to use what's called a matrix to help us solve a system of equations. In this video, we're going to discuss what a matrix is, try to give a little overview of the topic, before we get into the technique for solving systems called the Gauss-Jordan Elimination method, sometimes referred to as the Gaussian elimination method. We're going to talk about how we use this technique with what's called elementary row operations, and then we're going to see how we can apply some of our everyday technology to help us use this technique. Now, the first thing that we need to do is first identify what is a matrix. So it's a little hard to describe other than think of it as a way of storing information. We're going to define a matrix as an array of information. And this information can be things like, let's say, numbers. That's what we're going to be working with. It can be numbers, it can be expressions, it could be symbols, it could be a lot of things. So I'll just say etc. here. So it's an array of information, and an array is an organized way of presenting information, or I should say of storing information. So we're going to say a matrix is an array of information, and it's organized into a very specific way by using rows and columns. There we go. So a matrix is an array of information organized into rows and columns. So an array, and they sometimes refer to this as a square or rectangular array, is just a way of organizing information and storing it. This right here is a matrix. It is organized by rows and by columns. So things line up in rows and they line up in columns. And it's an array in that it has just collected information for us, okay? This by itself, it's kind of hard to know exactly what's going on here, other than we've just stored some type of information. Here we just stored a collection of numbers. Now, one other thing that we should know about matrices is the dimension of the matrix, or sometimes called the order. So I'm going to call this the dimension, because matrices can store all different types of information and all different amounts of information. Here we have 2 rows and 3 columns. You could have any number of rows and any number of columns. So we're going to say that the dimensions here really describe the row number versus the column number. And that's what the dimension of a matrix is. You got to describe how many rows there are and how many columns. So when talking about the dimension of this matrix, you would say whatever the row number is by the column number. And here what we're saying for this example is this is a 2 by 3 matrix. I've talked about the rows being 2 and the columns being 3. So when I tell you something like a 3 by 4 matrix, you could picture in your head something 3 rows down and 4 columns over. Now, I want to point something out that a lot of students tend to get confused about when it comes to dimensions, and they talk sometimes in books about things like a 3 by 2 matrix or a 5 by 7 or, any sort of dimension, you got to remember that it goes rows and then columns, because you don't want to get confused by a 3 by 2 matrix and think this is the same thing as this. These two matrices, this is a 2 by 3 and this is a 3 by 2. These two matrices are not the same. Okay, that's an important idea here. The dimension of a matrix is incredibly important. We unfortunately don't have much time in this video to really dive in deep to matrices and matrix operations and how we perform different techniques on matrices. But in a later video, we'll really try to dive into all the different concepts of a matrix and how they're used. And you'll see when you try to perform algebraic operations on them, like addition, subtraction, and especially multiplication, the dimension of the matrix becomes incredibly important. Now let's talk about systems of equations. And here we have this particular example, 2x minus y equals 5, and x plus 2y equals negative 5. Okay, we have multiple linear equations here. We got a system. We can take equations, and we can turn a system of equations into a matrix. The way in which we do that is by working with the coefficients of the matrix. That's really the important bit of information that we need to know. Now, first off, before you do anything, make sure, I'm going to put a big note here, make sure the equations are all in standard form. And remember, standard form is, let me write this a little neater. AX plus BY equals C. That's the standard form of a linear equation. You need to make sure that's the case, because what we want here is we want the X's to line up, the Y's to line up, and the numbers to line up. We are going to make a matrix where the rows represent the individual equations, and the columns represent the individual variable components. So here, if I turn this into a matrix, I would write 2, -1, 5, a 1, a 2, and a -5. I'm going to put square brackets around this. A lot of times, some textbooks use parentheses around them. I don't like to use parentheses personally. I'm sure they're easier to write, but sometimes parentheses get a little confusing. Not that it really matters. I just prefer square brackets. But right here, I've just taken these two equations and I've represented them with a matrix. The rows that we have here are the coefficients that were in the equation. Take a look here. The first coefficient was a 2. The next one was a -1. And then the constant term was a 5. So that's what I have in the first row. In the second equation, the coefficients went 1, 2, and then the constant -5. So that's what I have in the second row. It's important to have them in standard form because we want to make sure that everything in the first column is of the same variable. These coefficients worked on the x variable, and these coefficients worked on the y variable. You don't want them mixed up. You want to make sure that everything in the column was affecting the same variable, okay? And the things on the end here are the constants that the equations were equal to, okay? What we do with this is we put a line down in between to kind of separate where the variables were from where the constants are, okay? This little line right here just represents where the equal sign was in the equation. It's really just a visual cue. A lot of online programs don't actually draw this line. If you took a system and they put it into a matrix, you kind of have to do this yourself. Our textbook does this, but some books don't. You just kind of have to mentally picture where that line is, or take a little pencil and draw it in for yourself. What I want to point out in this matrix are a couple vocabulary terms. The first term is what's called the coefficient matrix, and the other term is the augmented matrix. Right now, let me point out that the coefficient matrix is the matrix made up of the coefficients to the equation. So the coefficients are 2, -1, and 1 and 2. This is the coefficient matrix. The augmented matrix is the matrix that pairs together the coefficient matrix with the constants that the equations were equal to. So this part on the left here is the coefficient matrix. The whole thing is the augmented matrix. So those are some vocab words textbooks use. I know our book uses them, so it's helpful to just keep in mind what these are. But it should be very simple to just take a look at a system of equations and be able to put it into a matrix. And we're only here working with the coefficients. And you might wonder why that is. Well, think back. Whenever we solved a system of equations, in particular using the addition method, we just always manipulated the coefficients. Those were the things that we needed to work with. So working with matrices here plays on this idea that it's really the coefficients, the numbers out front, that you need to work with. So that's the information that we're storing here. Now let's go ahead and actually get into solving a system of equations using a matrix. Now the technique we're going to use is called the Gauss-Jordan Elimination method, sometimes referred to as the Gaussian elimination method. It's credited to the mathematician Gauss from, I believe it was he lived in the 1800s. And really what we're going to do here is attempt to perform the addition or the elimination method using only the coefficients and the constants in the system. Because that's really, if you go back and look at what did we do whenever we would do the addition method or the elimination method, we just manipulated the coefficients and added them together, right? We tried to get a term to cancel out so we could solve for one of the other variables. All that we do is manipulate the numbers out front. So we're going to do the same thing here. The way we're going to do this is we're going to use elementary row operations. And you might be wondering what the heck are elementary row operations. And in particular, we're going to use these unknown operations to turn the matrix into reduced row echelon form. All right, hope I haven't lost you just yet. Because really these things are actually a lot more simple than they sound. Elementary row operations are 3 rules that you have for manipulating a matrix, okay? These are the rules. When you're working with a matrix, you can swap any 2 rows. You can go into a matrix and you can rewrite it by moving 2 rows. You can swap them entirely. You could also multiply a row by a non-zero number. So you can take a row in a matrix and multiply it by whatever you want, and multiply all the numbers in the row by that value. Just don't pick 0. And you can add a row to another row. You can combine rows together. You can add one row to another row, or you can multiply a row and add it to another. We're going to see how all 3 of these operations work. What I want you to keep in mind, these techniques for the elementary row operation, we've done them already. We've done these when we solved systems of equations using the addition method, okay? When we would multiply a row by a non-zero number, can you multiply an equation, both sides of an equation, by a number? Yeah, you're allowed to do that. That's the multiplicative property of equality. You can multiply both sides of an equation by whatever you want. So that rule's pretty obvious. What about adding a row to another row? Yeah, that's the addition method. And by saying, hey, you can multiply a row by something and then add it to another row, yeah, we've done that already. So these rules as you start using them, you'll realize they're actually not that different from what we've been doing. So let's go ahead and actually practice applying these techniques. Now here's the process for how we're going to go and actually use the Gauss-Jordan elimination method. First, what you have to do is write your system as an augmented matrix. So take your system, make sure it's in standard form, and put it into a matrix. Then you're going to use the elementary row operations to change the values of the rows of the matrix. Okay? There is no set in stone order or process for how you must use the elementary row operations. Every matrix is different, and every matrix requires you to use the rules differently. And you can do any which order you want, right? You might do some methods that might be longer than other methods, but just as long as you get to the final process, you're good. The final thing that we need when we're trying to manipulate this matrix is we need the matrix to be in reduced row echelon form. This phrase right here, reduced row echelon form, this is a term that we use to describe the final form we want the matrix in. So as you're using these three rules to manipulate your matrix, to keep changing it around and changing the numbers around, you want to stop when it's in this reduced row echelon form. That's when the diagonals of the matrix are all ones, and every other value, except those in the last column, are 0. Here's what I mean by that. Let's say we had the example, 2, 7, 5, -4, and 6, 2. This was something we worked on at the beginning. Let's just pretend this was a system, okay? So I have this system here, and what I want to do is I want to use my rules to manipulate this to get it to reduced row echelon form. That's when the matrix has the diagonal values all be 1. So that's a 1, and this is a 1. The other values are zeros. Now, the things in the last column could be any number. They could be 0, they could be whatever, okay? But this is the form that we want. This is reduced row echelon form. I'm doing a lot of talking right now, and I want to actually get into an example because it's a little hard to see without actually doing some of the process. So let's go ahead and let's try working through this example right here. We have 2x minus y equals 5, and x plus 2y equals -5. They're both in standard form, so what we should do is first take this system and put it into an augmented matrix. The coefficients are 2, -1, 1, and 2. So here's the coefficient matrix. We have the coefficients of x, and we have the coefficients of y. And then we're going to say, what are the equations equal to? What are the constants? The first one's equal to 5, and the second one's equal to -5. This right here is our augmented matrix. The first row represents equation 1. The second row represents equation 2. We are going to take this matrix, and we are going to use the elementary row operations to manipulate it to get in that reduced form. So let's take this matrix, and we need to start thinking how we can get the diagonal terms to be 1s. These spots right here need to turn into the number 1, while these spots need to become 0s. So how might we go about doing that? Well, one technique I'm seeing right away is if I want these to be 1s, I kind of want these spots to swap. So what I'm going to say to do is let's take row 1 and row 2 and swap them. So I'm going to move row 2 to the top, and I'm going to move row 1 to the bottom. There is one of my elementary row operations. I said you could swap row positions, so I just did. And hey, what do you know? I got 1s on the diagonal now. I'm starting to get there, okay. Now, let's try to think, how can we get these values to be 0? Now, I could just multiply this entire row by 0, but oh wait, I'm not allowed to do that. And that would get rid of the 1 there. So, no, I'm not going to multiply by 0. I can't really multiply by anything, and I already swapped rows. Swapping again won't do anything. So we're going to use the other technique, and this technique is used quite a lot. We're going to try to add the rows together, okay? I want this to be a 0. But if I add the 1 and the 2 together, I would get a 3. That's not going to work. So let's think, what could I do if I took row 1 and added it to row 2 to be the new row 2? Well, that wouldn't really work. So what could I do instead to get this to be a 0? Well, I could multiply row 1 by a -2. If I did that, I would take all of these values in row 1, multiply them by -2, and add them to the second row. So let's try to see what happens here. Notice that row 1 doesn't change, okay? I'm just changing what row 2 is here. So let's think. Let's take -2 times 1 and add that to 2. So what do I get? -2 plus 2 is, hey, that's a 0. So there we go, we have a 0 here. Now let's take the second column. -2 times row 1 is a 2. And let me add that to row 2, which is -1. So that's a -4 plus -1. That's -5. Well, okay, that's got rid of the 1 I wanted, but we'll see if we can keep working with this. Now let's work with the constants. We take -2 times what's in row 1. It's a -5. And we're going to add this to 5 in row 2. So we get a 10 plus 5, which is 15. What we did here was the addition method. We just added 2 equations together to get a new one, okay? So I'm just changing row 2 here. And I've added row 1 to it by multiplying it by something. This is the exact same thing as the addition or elimination method. So I now have a 0 right where I want it to be. Cool. I have a 1 where I want it to be. But here's the problem. That's a -5. Darn it, I wanted that to be a 1. Well, there's a pretty easy fix for that. Let's take row 2 and let's multiply it by -1/5. And that's going to be the new row 2. So row 1 stays the same, 1, 2, and -5. Let's take a look at the bottom now. 0 times -1/5 is, well, that still stays a 0. -1/5 times -5 is, hey, that's a +1. And 15 times -1/5 is -3. All right, I'm starting to get there. I have 1s on the diagonal. I have a 0 here. All I need is for this 2 to become a 0 as well. So let's keep going with this. Let's try and think, okay, there's nothing I can multiply 2 by to become 0. I don't want to swap the rows because that would just move the 1 up here, and that's not what I want to happen. Instead, I'm going to have to use the only other technique I have. I'm going to have to add row 1. I'm going to have to add row 1 and row 2 together. But how would I do this? Because if I add them together, this would turn into a 3. So I need to multiply one of them by something and add them together. What I'm going to suggest is multiply row 2 by -2 and add it to row 1 and make that your new row 1. So row 2 stays the same. It's 0, 1, -3. But what we're going to do is we're going to take every value in row 2, we're going to multiply it by -2, and we're going to add it to the first row. So let's take 0 times -2, and let's add that to 1. Well, that's just a 0, and when you add 0 to 1, you just get 1. So that doesn't change. Now let's take 1, we're going to multiply it by -2 and add it to 2. Well, that's -2 plus 2, that becomes a 0. So we're going to put that in for row 1. Now let's take the constant term, -3. We're going to multiply -2 and -3 together, and we're going to add that to the -5 that's in row 1. That becomes a +6, and if I add that to -5, I get a +1. This right here is the reduced row echelon form of a matrix. We have the diagonal terms starting from the top left, all of 1s. Everything else is a 0 except for the constant terms. Those don't have to be 0. They could be 0 or they could be any other number. Okay? Now you might be saying to yourself, why is this helpful? Why is it that we took our matrix, what we started with in the very beginning, and we moved that into this really specific form? How does this work for us? What we need to keep in mind here is that since we started in standard form, we're also going to end in standard form. Every time we manipulated this matrix, we had the same two pairs of equations. We just kept making them look different. We changed their coefficients around, but they essentially were the same, right? They were all equivalent to each other. When we end with this final matrix, it's also going to be in standard form. Remember that the first column represented the x's and the second column represented the y's. This column right here represents the x's and this column represents the y's. This row was equation 1 and this row was equation 2. Why don't we go and rewrite the equations? We started with 2x minus y equals 5. And we had x plus 2y equals -5. Our new equations say 1x plus 0y equals 1. And 0x plus 1y equals -3. Take a closer look. What is this telling us? Well, hopefully you're seeing that, really, since these cancel out, we just solved the system. X equals 1 and y equals -3. These values right here are the solution to the system of equations. We just solved for x and y. And we did this really by symbolically using the substitution, or I'm sorry, the elimination method, okay? All we did was we manipulated the matrix until we got it in this form. The reason we want it in this form is so that we have one variable equal to one number at a time. And when they're equal to the number, you can tell what the solution is. So this is a really fun, ingenious kind of way for solving a system of equations. Let's go ahead and try another example. This time I want you to pause the video and try for yourself. First, see if you can put this set of equations into a matrix, an augmented matrix. Then see if you can use the elementary row operations to turn the matrix into reduced row echelon form. That's the very specific term for the final form we want it to be in. And hopefully then you'll be able to tell what the solutions are to the system. So pause the video, take a couple minutes, and give this a try. All right, well, first off, hopefully you're able to take the system and put it into an augmented matrix. We have our coefficient matrix here. The coefficients, the first column being for those on the x, the second column being those on the y's. And we have over here the constant values the equations are equal to. So we have the first equation represented by the first row, and the second equation represented by the second row here. So with this augmented matrix, go ahead and keep working to make sure that you're able to use these elementary row operations to solve the system. I'll check back in with you in a couple minutes, and let's see what you're able to come up with. All right, well, hopefully you were able to try and work your way through applying these elementary row operations. Here are a couple techniques that I used to go through and simplify this matrix down. One of my goals is to first attempt to get the diagonals to be ones. And here, they were given to us right away. So I didn't really want to swap any rows around because if they're already ones right there, I'm going to go ahead and try to keep that. The next task is to really go and make these other values 0. And how do we go about doing that? Well, we're going to have to add rows together. And you're going to want to multiply one of the rows by some negative value to cancel out this 2. Here I picked multiply it by -2. And when I did this formula, I actually was able to get this to be a 0. Unfortunately, that changed to a 5. But that was easily undone. I just multiplied the second row by 1/5, so I got right back to the one I wanted. Now it changed my other number, but that's okay. I don't care about that. Then my next task was to just get this to be a 0. And again, I'm doing the same thing as before. I'm going to add these rows together, but first I need to multiply this 1 by something to cancel out with the -2. I chose +2. So if you run through this formula, you'll see that it really works to cancel out those other values. So that way we have 1s on the diagonal, and then everything else is a 0. Now, you might have done a different set of techniques with elementary row operations. You might have done several more steps than I did. Maybe you did them in different orders. That's totally fine. You're allowed to do as many steps as you want, just as long as, in the end, you get into this reduced row echelon form. Now, once it's in this form, we can go ahead and identify what the solution is. We have the x values here and the y values here. So we can say 1x equals -5 and 1y equals 8. So the solution to this system of equations is the point -5 and 8. Those two values, if you plug the -5 in for x and the 8 in for y, you'll have a solution to both of the equations. It's just these two values right here. And really, the more you do this process, the easier it's going to get. Now, we are using this process for a 2x3 matrix, right? 2 rows by 3 columns. Why don't we try, instead of just having 2 equations, let's try a system of 3 equations. Here you can see I have 3 equations, and each of them have to deal with an x, a y, and a z, or some combination or lack thereof of these 3 variables. So first thing I'm seeing right here is that my equations are all kind of mixed up. They're all in different order. So let's go ahead and let's put them in standard form. So when I go ahead and put this in standard form, I should get an x plus y equaling 5, a -2x and a minus y plus 2z equaling negative 10, and then a 3x plus 6y plus 7z equaling 14. With all of these equations in standard form, we can now go and try to put them into an augmented matrix. We're going to have 3 rows here because we have 3 equations. The first equation, let's try to have the x coefficients come first. So we have a 1. The y coefficient is a 1. The z coefficient, however, is 0, and it's equal to 5. Notice since there's no z in this first equation, its coefficient is being marked as a 0. So again, these are the x's, the y's, and the z's. So in the second equation, I have a negative 2 for the x, a negative 1 for the y, and a 2 for the z, and the equation's equal to a negative 10. The third equation was written already for me in standard form. It's a 3 for the x, a 6 for the y, a 7 for the z, and a 14 for the constant term. I'm going to go ahead and put my line break in there. And now I have my augmented matrix. Now that we have our augmented matrix, what I'd like to do is start using these elementary row operations to make sure that I get ones on the diagonal. And you can already see that I start to have some of those. Some ones are already there. But what I'd like to do is really use these operations to turn the other values that aren't on the diagonal into zeros. So let's go ahead and let's start trying to do some of that. First up, what I'd like to do is get rid of this negative 2 here. So what I'm going to do is I'm going to take 2 times row 1, and I'm going to add that to row 2 here. So let's add that to row 2, and that's going to be the new row 2. So row 1 stays the same. It's 1, 1, 0, 5. Row 3 stays the same. It's 3, 6, 7, and 14. All that I'm changing is row 2. So let's say, okay, 1 times 2 and add that to negative 2 is a 0. 1 times 2 is 2. Add that to negative 1, and that's a positive 1. Okay. Now let's go ahead and take 0 times 2, which is 0, and add that to 2. That's just still a 2, so that really didn't change anything. Now let's take 5 times 2, which is 10, and add that to negative 10. Oh, that becomes a 0. All right. So we got ourselves ones on the diagonal still, so I don't need to worry about that. And I got a term to become a 0. So looks like I'm doing pretty good so far. Let's continue this process, this time by making that 3 into a 0. So I'm going to do the same technique. I'm going to take row 1. This time I'm going to multiply it by negative 3, and I'm going to add it to row 3 to be the new row 3. This is a common technique for when you want something to be a 0. You take one of the rows, you multiply it by some number, and add it to that row just to cancel something out. It's helpful when one of the terms is a 1. So let's go ahead and say that the first row and the second row won't change, but the third row will. So let's take 1 times negative 3 and add that to 3. So it's negative 3 plus 3, so that's a 0, just like I wanted. That cancels out. Now let's take 1, multiply it by negative 3, and add it to 6. 1 times negative 3 is negative 3. Negative 3 plus 6 is a positive 3. Then we can do the same thing with the 0, but that's not going to change anything, because 0 times negative 3 is 0, plus 7 is just 7. And then, if I took 5 times negative 3, I get negative 15. If I had negative 15 and 14, I would get a negative 1. So there, I've gone through and I've done the exact same process, but this time I got the bottom left corner to be a 0. So I'm starting to get there, okay? The next tasks would be really to get these to be a 0, that to be a 0, and that to be a 1. So, well, looks like we're going to have a couple more steps that we're going to need to do. What I'd first like to do is, well, there's a couple things that we could try. Let's go ahead and maybe let's start by trying to make this 1 into a 0. So what I'm going to do is I'm basically going to subtract these rows from each other. I'm going to say take row 2, let's make it negative, and I'm going to add that to row 1 to be the new row 1. So I'm basically saying, okay, take 0, make it negative, well that's just 0, and add it to row 1, so that's 1. Take 1, make it negative, so negative 1 plus 1 is 0. Negative 2 plus 0 is negative 2. And then 0 plus 5 is 5. So nothing changed in that row. And we're going to keep row 2 the same. And you know what? I could write row 3 the same here. But what I'd like to do is I'd like to go ahead and get rid of this 3. So let's just do that step before I write it down. Let's go ahead and take this middle value here. Let's multiply it by negative 3 and add it to row 3. So what I'm going to do is I'm going to take negative 3. I'm going to multiply it to row 2, and then I'm going to add that value to row 3 to be the new row 3. Okay, so let's take negative 3 times 0 and add that to 0. Well, that just stays 0. So that one's pretty obvious. Now let's take 1 times negative 3 and add it to 3. That becomes a 0. Then we can do the same thing with 2. 2 times negative 3 is negative 6. Negative 6 plus 7 is, hey, that's a 1. That's what we wanted to happen. And then let's go ahead and take a look at this last one. 0 times negative 3 is 0, plus negative 1 is still just a negative 1. So we're almost there. Let's go ahead and try to make some more room here. And we want to see the final steps are to just get rid of these 2's and to make them 0. So here's the last rule we used, where we changed row 3. What I'd like to do now is to get these to be 0. So I'm going to multiply row 3 by a 2, or I should say negative 2 to get rid of that one, and a positive 2 to get rid of that one. So let's take row 3. I'm going to multiply it by 2, and then I'm going to add that to row 1 to be the new row 1. And to get rid of the 2 in the second row here, let's go ahead and do the same process. This time, let's multiply row 3 by negative 2 and add it to row 2 to be the new row 2. So we're going to do a couple steps all in one here. So keep in mind, row 3 is not changing. The only things changing are row 1 and row 2. So we still have 0, 0, 1, and negative 1. But now we need to think, what's the rest going to be? So let's start with the first one. We took 2 times row 3 and added it to row 1. 2 times row 3, 2 times 0 is 0, plus 1 is still just a 1. So nothing changes there. 0 times 2 plus 0, well that's still just a 0, so nothing changes there. But then here's what I wanted to happen. 2 times 1, I'm sorry, yeah, 2 times 1 is 2, and then add that to a negative 2, that becomes a 0. And then in the constants at the end here, we have negative 1 times 2 is negative 2. When I add that to 5, I'm going to get a 3. And then let's go ahead and figure out what row 2 is going to be. Row 2 is a similar process and the same technique. We're going to say take 0 times negative 2, add it to 0, and we're still going to get 0. Now take 0 times negative 2, that's 0, and add it to 1, you still get a 1. Then let's take 1 times negative 2, that's just negative 2, add it to 2, you get a 0. So it worked just the way I wanted it to, where it canceled out these values. Oh, and let's not forget, negative 2 times negative 1 is positive 2. Positive 2 plus 0 is 2. So what we've done here is we have just put this in reduced row echelon form. We have ones on the diagonal starting from the top left, and every other term is a 0 except for the coefficient, or I'm sorry, except for the constants at the end here. Remember, these were all the x's, these were the y's, these were the z's. So we have 1x equaling 3, 1y equaling 2, and 1z equaling negative 1. So we could write our answer, and this time as an ordered triple, 3, 2, negative 1. That's our final answer. Hopefully this is starting to make sense to you. You can see how really we're just using a process of slowly manipulating the different numbers. You're hopefully seeing that, okay, there's some pretty common techniques I'm going to use for most of these problems. And what I'd like you to do now is try to use these problems to solve these two equations, or these two systems of equations. Pause the video and take a couple minutes to see if you can solve these, and then try to see if you're understanding the answer that you're getting. So pause the video, take a couple minutes, and then we'll come back to check our rather unique answers to these problems. All right, well, hopefully you were able to try to use a couple different techniques to get to your answer, but hopefully you noticed that you always ended up, no matter which row operations you used and in what order, you always ended up in the same situation. Let's take a look and see if we can replicate some of our work here. What I first am noticing is this problem has some fractions in my matrix. They have fraction coefficients, so there's fractions in my matrix. I don't like that. So what I'm going to do is I'm going to say, you know what? Let's take row 2 and let's clear the fractions. Let's multiply everything by a 2 here. Okay? So that suddenly becomes the new row 2. So it should be a 1, a negative 3, and a 4, because row 1 doesn't change. But row 2 is going to be 2 times a half is 1, negative 3, and 4. Well, that's interesting. The two rows are the same. Huh. Well, you know, that's okay. Let's just go ahead and let's keep doing our techniques here. Let's go ahead and maybe let's try to get this 1 into a 0. Right? Because we want these to be 1s while the other things become 0s. So let's go ahead and give that a try. What I would like to do is, well, let's take row 1, we'll make it negative, and we'll add it to row 2 to be the new row 2. Basically, we're subtracting the rows. So row 1 stays the same, but we're going to take the values, make them negative, and add them to row 1. So negative 1 plus 1 is a 0. Hey, that's what I wanted to happen. Cool. Negative 3 is positive 3, and positive 3 plus negative 3 is, oh, that's a 0 too. Okay, and if I took 4 and made it negative, it's negative 4, and add it to positive, that's a 0 as well. Uh-oh. I'm kind of in trouble here. I have a row of all zeros. And there's not really anything I can do to turn it back into a 1, is there? So here's a situation that we come across. In a situation like this, where the second row of this matrix really is the equation 0, well, I'll write it fully, 0x plus 0y equals 0. Or, more simply, 0 equals 0. This is an identity. This is a true statement. This means that our system is dependent. It is a dependent system, meaning these two equations right here are the exact same equation. We see that in the matrix where both rows are identical. The two equations here are the exact same. If you graph these, you would have the exact same line, one on top of the other. So, since this is a dependent system, since we have an identity, which is a true statement, we can say that there are infinitely many solutions. There are infinitely many solutions to this. Because when we solved the matrix, when we started manipulating it to get it into the form we wanted, we came across an identity. And we can't get out of that system. There's no way we could turn this into reduced row echelon form. It's just not going to work. Now let's take a look at the next system of equations. What I want you to do is, now that you kind of are understanding this unique system and setup, see if you can resolve this one and try to understand what the answer you're producing might be telling you about the system. All right, well, as I first work, I want to make sure that I'm able to put this into an augmented matrix. So I took the coefficients of the first equation here, 1, 3, and have the constant 2. And then I took the coefficients of the second equation, the -3, the -9, and the 1, and put those as the second row. Remember that these are the x's and these are the y's. So let's go ahead and try to put this in reduced row echelon form. Well, I want this to be a 0. So I'm thinking take row 1, multiply it by 3, and add it to row 2 to be the new row 2. So row 1's going to stay the same. It's 1, 3, and a 2. But what I'm going to do is, let's take these values, multiply it by 3, so 1 times 3 is 3, and add it to -3. That's a 0, just like I wanted. Now let's keep going. Let's take 3 times 3, which is 9, add it to -9, and oh, that's a 0 here as well. That's not really what I wanted to have happen. I didn't want them to cancel out, so maybe this is going to be a similar situation before where I get an identity, and I might have infinitely many solutions. Let's take a look. Let's try the last one here. 2 times 3 is 6, and 6 plus 1 is a 7. In this situation, I kind of have a different answer, don't I? Let's try to write these equations. I just took this system and I manipulated it to get x plus 3y equals 2 and 0x plus 0y equals 7. Well, there's a problem here, and it's with this second equation. 0x plus 0y is 0, and I'm saying that's equal to 7? No, that's a contradiction. I'm doing my work here and I ended up with a contradiction. Similar to when we would do things with the addition method or the substitution method. If you came across an identity, you would say, oh, I'm going to stop my work. There's infinitely many solutions to here. However, if you came across a contradiction, like in this case, you would say there is no solution. There is no solution to this system of equations. The reason is because these lines are actually going to be parallel to each other. You can actually test this out. Put these lines into Desmos. You'd see they're going to be parallel. They're never going to intersect. So we end up with a contradiction when we try our work, and we can say there's no solution to this. So these are the special case circumstances that you'd see as you work through using matrices to solve your systems. Now, hopefully, this technique of using matrices and this Gaussian elimination method, or the Gauss-Jordan elimination method, is making sense to you. And hopefully you're seeing, okay, this could be pretty valid as a technique for solving a system of equations. But let's be honest, a lot of you are probably thinking, oh great, another technique for me to memorize when I already have a bunch of other techniques, right? I have substitution, I have elimination. Why would I go ahead and just have this new technique, this matrix method, and I have to do all these like combinations of rules? Well, one of the benefits to this matrix method is it's really helpful when you have large systems. For example, when we had a system of 3 equations, you should remember from previous sections that when you solve a system of 3 variables, it's a very lengthy technique. You got to pick 2 equations, cancel out a variable, pick 2 other equations, cancel out the same variable, and then the equations that you get from canceling out that variable produce a new system that you need to solve to cancel out another variable. And oh gosh, I'm confusing myself just saying all of this, right? It's a very lengthy process. If you had 4 variables, or 5 variables, or 6 or 7 or 21, whatever, however many variables and that many equations, you would start to get pretty lost. It would be very lengthy. However, if you use elementary row operations, is it kind of tedious? Yeah. But is it that complicated of an idea to use? Not really. It's pretty straightforward to just keep making certain values 0, so do what you need to make them 0, and to keep everything diagonal as a 1. So hopefully you're seeing, okay, there's some validity to this. What I'm going to tell you now is what most students get mad at me about. And that is, we can actually use technology to help us out. We can use technology like a TI-84 or some type of graphing calculator to basically take our coefficient matrix, the thing that we want in this reduced row echelon form, and it will put it in that form for us. We can use the calculator to skip over having to do all these elementary row operations. Because yeah, it can get kind of tedious and time consuming. But if we put it into our calculator, if we take our original matrix and put it into a calculator, we could save ourselves an incredible amount of time and solve a system in merely seconds. Let's go ahead and let's take a simple example. Let's say 2x minus 3y equals negative 13, and 3x plus y equals 8. Well, we could put this into a matrix, and we would have the matrix 2, negative 3, negative 13, and 3, 1, and 8. There's our augmented matrix. This part right here is the coefficient matrix, just a little vocab for you. So what we want to do is we can use elementary row operations to put this into reduced row echelon form. And it wouldn't take us too long, but let's go ahead and let's try using our calculators for this. Let's use some technology. So I'm using a calculator app here that really is trying to mimic the TI-84 and other Texas Instrument graphing calculators. What you can do with your graphing calculator is this. We want to access the matrix menu. See right here on the left-hand side, this button for matrix. Your calculator has it labeled on the left-hand side as well, but notice that it's in the top corner here. Notice that all of these keys have little symbols in the top left corner. That's because your calculator can do one thing, or you can access the other option. So to get into the matrix, the thing in the top left corner, I'm going to hit second, the blue button, and then I'm going to hit the matrix button right here. Now, I'm in the matrix setting on my calculator. What I want to do is go over to Edit. You'll see that I have a bunch of matrices here. They're labeled matrix A, B, C, D, E, F, G, etc. I can pick any one of these, so I'm going to pick matrix A, and I'm going to edit it. First off, I need to tell the calculator what are the dimensions to this, how many rows and how many columns are there. So this had 2 rows, and how many columns? It had 3 columns. So it was a 2 by 3. And there my calculator has gone and actually created a 2 by 3 matrix. Now it wants me to fill in the matrix. So in the first top left portion, the number was a 2. In the middle part of the top, it was -3. And then the constant that it was equal to was a -13. The second row was a 3, a 1, and an 8. So there, I've just gone and I've entered in the matrix. You'll notice that it doesn't have a line drawn like in our augmented matrix. And again, that's fine. Your calculator typically won't do that. You just have to imagine it for yourself. Let's go ahead and let's go back to the home screen now. So what I'm going to do here is to get out of the matrix menu, because we just stored this matrix. We typed it in into matrix A. I'm going to hit second, the blue button right here on the left-hand side, and then I'm going to hit the button next to it for quit. This takes me back to the home screen, okay? What I need to do now is I want to get back into the matrix menu. So let's go second, and I'm back into matrix. Here, I last left off where I was in the Edit tab. Let's go to the Math tab. This is a collection of formulas all built into your calculator that allow you to perform different techniques on your matrices. Look all the way down at part B, the RREF. Look right above it. There's part A, which is REF, and part B, which is RREF. RREF stands for Reduced Row Echelon Form. You want the one that has the 2 R's in it. The one that has just 1 R is called Reduced Row Echelon. It's called Row Echelon Form. The 2 R stands for Reduced Row Echelon Form. The one with 2 R's is the one you want. Okay? So I've just hit that option, and it said, okay, you want to take a matrix and put it into RREF, Reduced Row Echelon Form, that form that we really like that tells us the answer. But notice it tells me, okay, but you have to tell me which matrix you want to perform this task with. So I need to input a matrix. So I'm going to go back into the matrix menu. I hit second, and then the matrix option. Now go over to the Names tab. In the Names tab, I need to select which matrix to use. Here, I stored matrix A as the one I was working with, so I clicked A, and it says, okay, we're going to perform this task, the RREF, the Reduced Row Echelon Form, on matrix A. Now let's go ahead and hit Enter to see what we get when this new matrix that we have, this matrix A, has simplified into the form that we want. You'll see that the matrix we get is 1, 0, 1, 0, 1, and 5. So we had the matrix 2, -3, 3, 1, and the constants were -13 and 8. By performing RREF, by performing this operation, we ended up with a 1, a 0, a 0, 1, and a 1, 5. You can put that little line in to represent the augmented matrix if you'd like. But go ahead and notice that this tells us the answer. We know the solution to this system. X is equal to 1 and Y is equal to 5. That's our answer. It's the 0.15. So we can solve a system of equations using matrices really in seconds. The only time that it requires is how long does it take you to type in a matrix. So why is this helpful to us? You could say, yeah, but I could just as quickly perform the elimination or the substitution method. Well, now think back to the 3-variable system. Think back to how long those problems would take you, right? And how susceptible to mistakes we were. If you have any comments about the video or any questions about the math that we did or things that were brought up, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought or if you have any questions, and until next time, take care.